So in this video, we're going to figure out the maximum area of an isosceles triangle inscribed in a fixed circle. So here we have a circle, a fixed circle, a circle with the radius of 5, where there is a triangle, isosceles triangle inscribed. So inscribed means the vertices or the corners of the triangle make contact with the circumference of the circle. And in this case, we want to figure out the ideal area, the maximum area, the biggest triangle isosceles that you can fit inside the circle. So in this triangle here, I'm dragging the base of the triangle and I'm changing the dimensions, the size of it. And ideally, you want to find the biggest size. In this case here, we do not see the area. The area is not calculated, unlike the previous example where I talked about the rectangle in a circle. So the idea is, how are you going to calculate the area of a triangle and somehow link it to one of the dimensions in the circle? So here we're going to maximize the area of a triangle. So the area of a triangle, first things first, let's write down what we know about the area of a triangle. It is base times height divided by 2. So we're going to have to develop a function in regards to A, so area, either in terms of B, expressing a function in terms of B variables, or a function expressed in terms of H. So let's actually go back to our diagram and look at the base. It's just labeled. So over here, from here to here is the base, and from here to here is the height. Now the question right now is, there's something about the circle that's connected to one of the features of the triangle. Now in this case here, we only know something about the radius of the circle. So the radius of the circle starts from the center and actually goes to the top. So we know from here to here is going to be 5 because the radius of the circle is 5. Now from here to here, the height we don't know. So I'm going to call this part here x. So that little piece is x. The radius is also connected from the center to the edge. So from here to here is also 5. From here to here is also 5. So when we develop the function, it seems like when we change the size of the triangle, the height is changing. So if this is taller, then what's going to happen is that the x will get bigger, or if we take this and move the base up, then the x will be smaller. So in this case, we have an extraneous variable, which is indirectly connected to the height over here, and indirectly connected to the base. And now the question is, well, Miss, how is this vertical connected to the base? Well, again, very similar to the rectangle inscribed in a circle. Do you not notice that there is a right angled triangle? So we do have a feature here that does not change when we change the shape of the triangle. There will always be a right angled triangle. And what's the relationship between 5x and half of the base? Pythagorean theorem again. So over here, I'm just going to write down on the right-hand side the constraint. So put here the constraint equation, which will not change, is that we have 5 square is equals to x squared plus half the base square. Because from here to here is not the full base, it's half, okay? And over here, I'm just going to clean this up, and we get x squared plus b squared over 4. And I'll clean this up. I'm going to put here, multiply everything by 4. I have 100 is equals to 4x squared plus b squared. So this is our constraint. So sometimes when you have a constraint, it's kind of, there should be, it should tell you which function you're going to express the function in terms of. Is it a in terms of b or a in terms of h? And when I look at this constraint here, I can see that right away I can isolate b easier. I could isolate for x, but if I have isolate for x, then I'm going to get fractions, which I kind of want to avoid. So I'm going to isolate for b. In other words, b squared is equals to 100 minus 4x squared, and b is equals to square root of 100 minus 4x squared. So I'm going to take this constraint, and now I'm going to say, okay, all right, so let's actually express this in terms of x. So, okay, so over here, I'm going to go back to this function here. So I'm going to write that a is equals to bh over 2. So the question right now is, I cannot express a in terms of b or h because I introduced an extraneous variable x. So in this case, I'm forced to express a in terms of x I mean, I don't have to, but I'm going to show you using an extraneous variable. What is the base? Well, what's the height first? Well, the height is from the top to the bottom. In this case, it's 5 plus x. So the height is going to be, in bracket, 5 plus x, all divided by 2. And what's the base? Oh, we have it. It's from our constraint, and that's going to give us 100 minus 4x squared. So just to write it more nicely on the bottom left-hand side, this is our function we're going to have to optimize. I'm just rearranging some pieces here. 100 minus 4x squared over 2. So now we're going to have to figure out the restrictions for x, what x cannot be. So let's have a look at the diagram here. So over here, let's actually grab this and see what we can do here. So let's have a look at x. So right now, if I put the triangle like this, that means the height is the same thing as the radius, meaning that the x is 0 because we have no extra piece to it. But if I push it down, what happens? Then x starts to emerge. In this case, x is going to be 2, x is going to be another 4, and over here, when the height is maximum, well, close to 10, the size of the diameter, then the x is going to be 5 because 5 plus 5 is 10. But the thing is, so it seems like x can be no more than the radius of the circle. But however, some students might argue, well, miss, does it have to be like above 0? Because it seems like everything is always above 0, like for example, the width and the length. However, if I push it back, what happens to the height of the triangle? It's less than 5. By how much? Well, because x is the distance from the center of the circle, from here to here, is also x. But in this case, what's my height? It's going to be backwards. So in other words, x could be very, 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 very small. In this case, we're going backwards. Over here, this is plus x because we're adding to the radius, so 5 plus an extra piece. Or we can actually go backwards and 5 minus. So this dark line, this area over here between A and B, is the x, but we're going to subtract. In this case, how much x can I subtract from 5? Well, you can subtract the entire one. In other words, the x can be plus 5 or minus 5, just based on GeoGebra. So I'll put here on the side, I'm going to put here x is between 5 and negative 5. It cannot be equal to 5 because if x was 5, that means your height would be 10. And there's no way that the triangle could have a height of 10, because if it did have a height of 10, it would be the maximum diameter, meaning it wouldn't have a width at all, meaning there will be no base. Now, how do we take this from an algebraic point of view? Again, very similar to the previous one about the rectangle inscribed in the circle. We want the area to be positive. In other words, we're going to have to solve for the inequality and solve for the zeros and the inequality. So in this case, I'm going to put here x plus 5. I'm just going to rewrite the question out again really quickly. Over 2 is greater than 0. We're going to have to set up an interval table chart here, but before we do that, we need to solve for the zeros of every single piece. So in other words, the numerator will provide us all the zeros because the denominator has no x. So in this case, x plus 5 is equal to 0. 100 minus 4x squared is equal to 0. This gives me negative 5, and this gives me, I move the 100 over, divided by negative 4. That gives me x squared is equals to 25. Or I skipped some steps. X equals to plus minus 5. So in other words, x here, all right, I'm going to put here all the factors of the function. 100 minus 4x squared. I'll put the 2 as well. It doesn't really matter if I put the 2 or not. I'm going to put in the zeros, which in this case, negative 5 and 5. And keep in mind, we want the area to be positive. We're looking for the positive. All right, so let's actually sub in a number. So 2 here will give me all positive, so it doesn't really matter what happens here. All right, I'll put here a line here. This gives me zeros. All right, we're going to have to figure out the signs in between. All right, so let's actually put a number in between, for example, negative 5 and 5. Let's put 0. All right, when x is 0, what happens? Well, this gives me a positive. This gives me a positive, and overall I get a positive. Great. What happens if I put a number that's like, for example, like 6 or 7? Well, if I put 6 in here, I get a positive. Great. But if I put, for example, like 6 in here, what happens? I'm going to get a number that does not exist, because if you put a number in here such as 6, 6 times 6 is 36 times 4, which is bigger than 100, meaning you cannot take a square root of a negative number. It doesn't exist. Over here, what happens if you sub in negative 10? I get a negative number, and you can pretty much stop here because remember x plus h is the height. We cannot have a negative height. But if you decide to keep on going, you keep on going, you get a negative well, sorry, not available, because if you put, for example, negative 10 into here, you're going to get a negative square root, which you can't. So this is not even available at all. So that's why this is our restriction, just showing you from the algebraic point of view. So in this slide here, what I did was I actually typed in Desmos, the function that you're optimizing. So this is the function that we developed. And over here, this is the graph. So in this case, this would be the area of the triangle, and over here is your x, that little piece you're adding on or subtracting to get the height. All right, so if you look at here, the domain, even the graph actually tells you the domain. The domain is from -5, and that's 5, and the graph is actually between our restrictions. And based on this, where's the absolute maximum height or maximum area? Well, the tallest area is the maximum y value, or the dependent variable. In this case, it's over here. The answer is somewhere around 30 something, 32-ish, give or take. At what value? The x is going to be around, I don't know, around like 2-ish, give or take. So Desmos will tell you the answer if you actually typed in the function in there. But of course, we're going to have to rely on the algebra, which I'm not going to spend too much time on, unlike the previous video with the rectangle and the square, because the function is very similar. If you look at the function here, right over here, it's very similar. This is a product. So if you want to find the derivative, what are you going to do? You're going to have to take the derivative using the product rule, meaning here's your left prime, here's your left and right. The 2 doesn't matter, it's a constant. So just be aware that derivative rules, when you have a constant, you just have to write it outside here. It doesn't make a difference. And then you take your derivative. So in this case, you take x prime, and then you just leave your square root. And then the next one is you take your you take the derivative of this piece here, 4x squared, put a bracket prime, and then you take x plus 5, and that's it. So you don't have to use quotient rule, all right? And now in this case, just like similar to the previous example, you have to change this to a power rule. You take your chain rule, power rule, and then you clean it up. So over here, you're going to have to clean up. And if you don't know how to clean up, I suggest you go to the previous video about the rectangle inscribed in the circle. That describes everything. Once you get your critical point, so you have to set a prime to equal to 0 and undefined. I think you're going to get a fraction, a rational type function. You get your critical points, you do your first derivative test, and then after that, once you figure out your critical points and showing your first derivative test, then you're going to have to check your endpoints. In other words, I'm not going to go into detail, so just make sure that ideally you want to figure out what happens as you approach -5, what happens to the area of the triangle as you approach -5 when that little piece is subtracted from the height versus this piece here. So as I said, these videos will get shorter because I'm not going to go through all the technical details. And if you did this, it should be plus, and this should be from the left, this should be from the right. And then you should get 0 as your end behaviors. And then at the end, make sure that you put in your critical point and you get your maximum area. So I think whoever's looking at this video, I think you should go through the motions of the algebra, finding all the derivative, cleaning up, and type this into Desmos, and just Desmos will tell you what the answer will be.